Welcome back everyone to another episode of the Reading Club, and in today's episode we will continue covering Presolve Reductions in mixed integer programming. Right, so this is part 5. So in the first 4 part, what all things we covered, let me just briefly summarize those things. Right, so in the first 2 parts, part 1 and 2, we covered Presolve Reductions that look at one constraint at a time, and in part 3 we looked at one variable at a time, right? The Presolve reductions which will only look at one variable at a time and try to do some reductions on them. And in part 4 and 5, so part 4 we just released last week, and in this one we are going to look at multiple variables at a time. Multiple constraints at a time. Okay, so this all parts we have already released before, so if you haven't watched them, you can watch them. The links will be in the description. And this is part 5, right? So this is where we are right now, and we will finish off with Presolve reductions that look at multiple constraints at a time. Okay, so before that we have seen 3 Presolve reductions in part 4, and in today's episode we will see 2 more. Okay, so let's get started. Okay, so we are going to start with bound and coefficient strengthening. Right? So this is something that actually we covered the basics in part 2. Right? So if you haven't watched this part 2, then I'll recommend that you watch this first, because I'm going to build up on top of what I covered in part 2. Okay, so if you have watched the part 2, then let's jump into what we can do about bound and coefficient strengthening when we are looking at multiple constraints at a time. Okay, so in part 2 we saw that we can break down one constraint like this, right? So we have AI, right? So this is one subset which is S XS plus the rest is the one variable that we are actually trying to tighten the bounds or coefficient, right? So AIK XK, this is what we looked at, right? So here we are trying to strengthen this coefficient AIK, or we are trying to change the bound of this variable XK, right? So if XK is integer, then we can sometimes even change this coefficient as well, but otherwise we can definitely change the bounds of XK, right? So all of that actually dependent on this part, right? So this part's bound. So here we have LIS is less than equal to AIS XS and UIS, right? So this is the lower bound and upper bound of this part, and depending on how tight this lower and upper bound are, we can tighten this coefficient or change the bounds of XK, right? So that's the idea. So entire focus is about finding good quality lower and upper bound for this part. And what we used in case of single one constraint at a time was infimum here for the lower bound and supremum here for the upper bound, right? So this is something that we covered in part 1. What is infimum? It's basically the smallest value this expression can take when we are looking at the variable bounds only, right? So if the coefficient is positive AIS, then we look at the corresponding variable's lower bound. If the coefficient is negative, then we look at the corresponding variable's upper bound, right? So that's how we compute infimum, and similarly we compute supremum. And these are like very easy to compute. They don't really require a lot of computation, right? So, but they are not the tightest lower and upper bound with respect to the entire MIP, right? So that's where we can improve when we are looking at multiple constraints at a time. So what is the tightest lower bound we can achieve? So we can basically solve the entire MIP something like this, right? So we basically want to minimize this part, which is AIS XS, right? And this is what we'll minimize subject to our entire MIP, right? So AX less than equal to B, and yeah, X is between bounds U and L, and some X are integers, right? So this is our entire MIP, and if we just, these are our regular constraints, we just change the objective completely to this expression so that we obtain the smallest value that it can take with respect to all of these constraints, right? So this is the tightest possible lower bound for this expression. Similarly, if we just maximize this, then we obtain the tightest upper bound. Now the problem with this is that it basically requires me to solve the exact same MIP, right? So this is something roughly the same MIP. The objective has changed, but more or less all the constraints are there, and it is super complex, right? So it is as complex as solving the original MIP that we are trying to solve faster. So definitely we are not going to do this. So what we can do is, as an alternative, is that we can basically drop this constraints, right? So drop this integrality constraints. So then it becomes a linear program, LP, and it is significantly faster to solve, but it is still super expensive, right? So we are trying to tighten bound of one variable, and there are like a lot of constraints, and for each constraint we are going to find one subset, and for every subset like this, we are going to solve two linear programs, right? So one for maximization, one for minimization, to find the lower and upper bound like that, and that is still super expensive, right? So what we want to do is that we want to drop some more constraints, right? So to make this part slightly more efficient, and all of these bounds are way tighter than this infimum and supremum, right? So always it is always helping us, but at the same time it is taking a lot of time. So here we basically consider all constraints. Instead, we can consider a subset of these constraints, right? So that way we can reduce the size of this LP, and this LP will be like faster to solve. A particularly interesting case will be when we have only one constraint, right? So let's take a look at this. We are minimizing AIS XS subject to, let's say we keep only one constraint, A J X is less than or equal to BJ, right? So this is something kind of has a similar structure to knapsack, right? Knapsack, we have maximization objective, but pretty much otherwise it's kind of similar structure. And this kind of problems, just objective and only one constraint, this is kind of studied in literature. It has a special structures, some special algorithms already exist, so this can be solved in order n time, right? So where n is the number of variables. So this is kind of efficient to solve, and it will give us tighter bounds than this infimum and supremum, because they are not really looking at this constraint, right? So that's the key idea behind having tighter lower and upper bound, and using this lower and upper bound we can obviously use the same process that we described in part 2 to tighten the bound of xk and aik. Okay, so that's one part. What Gurobi does is something even more than that, right? So they basically, what they do is that they break down this part into more parts, right? So this is one part, but they can say that let's break down this one into AIS1 XS1 plus AIS2 XS2 and so on and so forth. XSSD. Okay, so these are this single part is now broken into D parts, and for all of them you can find the lower and upper bound, right? Most of them you will find lower and upper bound using this infimum and supremum, and like overall lower bound and upper bound for this expression is just, you just add up this lower bounds, right? So if you add up all this lower bound, then you get a valid lower bound for this entire expression. Same for the upper bound. Okay, now what's the point of doing this is that sometimes we break down this parts in such a way that one of this part has a special structure, right? So let's say this part, right, this part has some special structure, so that solving either this entire MIP or LP or even this small part, right, it's way more efficient for this kind of expression in the objective, right? They haven't really described what special structure they look at, but that's the idea, right? So most of them they use simple infimum and supremum, most of these parts, but for one or two parts, or sometimes more than one two parts, they use this their special structure to solve this complex MIP or LP, and get a tighter upper or lower bound for that, right? So that's the idea behind it. Okay, and why exactly we are focusing on this part at all, right? So we can straight up focus on this part, right? So we are basically trying to tighten this bound of this xk variable. Then why are we minimizing or maximizing all of this instead of we can just simply say that let's remove all of this and just minimize or maximize xk, right? So that's directly optimizing our bounds for this variable. And that is also something that we can do again, like sometimes we can consider entire MIP, sometimes we can consider LP or part of the LP, again all the tricks that I just described, right? So all of that they do, but like they do it very rarely, right? So this is not done for all variables. They are like, they sometimes do it, and that's the idea behind bound and coefficient strengthening when we have access to more than one constraints in our MIP, right? So that's so let's talk about the impact, right? So how much this helps. So in the benchmark they listed, it speeds things up by 6% on instances that require at least 10 seconds to solve, and it has even more impact that they haven't highlighted it, but in the table it seems that it improves performance by 22% on harder instances, right? So those instances which require 1000 seconds to solve, at least 1000 seconds to solve, right? So for those instances, this multi-row bound and coefficient strengthening improves the performance by a very large amount, right? So this is obviously super important, and this is on top of single row bound and coefficient strengthening, right? So this improvements, right? So they are significant improvements. Okay, so the next one we are going to look at is called clique merging. Clique merging. Right, so what is that? So let's take a look at some particular types of constraints which are on binary variables. Okay, so let's say we have x1 plus x2 is less than or equal to 1. Here we have x1 plus x3 is less than or equal to 1, and we have x2 plus x3 is less than or equal to 1. So all of these are binary variables, right? So sometimes instead of x2 we have 1 minus x2 or 1 minus x3, but that's kind of easy to replace, right? So we are going to look at this kind of constraints, right? So these are more like packing type of constraints, right? So this is basically at most one of them can be packed in our bag, at most one of them can be packed, it's things like that, right? So these are also called the cliques, right? So if we have more than two variables, then it will be easier to verify, but the idea is that only one of these two variables can be selected. Same for these other two, right? So overall, if we look at all of this constraints simultaneously, then we can merge them into a single clique, which is x1 plus x2 plus x3 is less than or equal to 1. Okay, so that's called clique merging, right? So exactly only one of them, these three variables, can take the value 1 as far as these three constraints are concerned, which is also represented by this single constraint, right? So you can verify that by yourself. It's simple clique merging. This idea is not new, but it's kind of the implementation of this clique merging is super interesting, right? So it is very, very complex, and how do we basically manage all these cliques, and how do we actually detect all this 1, 2 and 3 constraints, and then come up with this kind of a constraint, right? So basically what they did is here we extended this clique, right? So here it had only x1 and x2, and we say that now it will also have x3 in it, and yeah, so that's one clique was extended, and these two cliques, right, they were basically dominated or consumed or reduced or something, whatever, right? So they are now redundant after we have this extended clique, and so they basically can be removed from the model. In fact, all three of them can be removed. We can just keep this one only. Okay, so that's the idea. Like, so how do we detect this? What kind of data structure we use to do this kind of operations? That's all the interesting parts, right? So first of all, we can have a click graph, right? So a conflict graph or something like that, right? So we have vertices for every variable, right? So, and whenever we detect this kind of a structure, right? So here it is x1 and x2 are in conflict. So we add one edge for x1 and x2. Only one of them can be set to 1. Similarly, we'll add one edge for x1 and x3, and then one edge for x2 and x3, right? So this is x1, this is x2, this is x3. So we have this complete click graph here, and based on this, we can just simply write this one, right? So that's called the conflict graph, right? So for every click we have of size L, right? So how many edges we will have? We'll have L times L minus 1 by 2. This many edges we will have, and we will have to store all of these edges in our graph, right? So this is this basically is a storage issue when L is large. So storage is a problem when we have longer clicks, and so this becomes like this will basically consume a lot of memory. So what we can do is consider doing our click merging operations on the constraint matrix itself, right? So this matrix itself, where we have ones and zeros, and if we use a sparse representation of a matrix, then we don't really need to store all the zeros, and we only store where we have non-zeros. Okay, so here we can have constraint matrix, but let's take a look at what's the easiest way to detect this kind of do this kind of operations, right? So first of all, we'll need to find out the neighbors of every vertex, right? So for doing this kind of graph operations, so let's take a look at, if you want to look at neighbors of x3, then what we'll have to do is we have to look at the column x3, right? And it has two non-zeros, this one and this one. For every non-zero, we have to look at this corresponding row and find out the non-zeros on this rows, right? So all of those are neighbors of x3. So we have x1 here as a neighbor of x3 and nothing here on x2, and yeah, so that's one neighbor we found here from this constraint. And here also we have a non-zero, so we also have to look at this constraint, and here again, like, we find one non-zero here, and that's how we find the neighbors of x3. So on an average, this operation, they have mentioned that it requires LC bar, which is average number of non-zeros in each column, plus LC bar times LR bar. So LR bar is average number of non-zeros in each rows. So that many memory access it will require to find out just the neighbors of one variable, right? So that's kind of large. Okay, so here the problem is not storage. Here the problem is access, right? So rather number of memory access that we perform, right? So this is large for this kind of cases, right? So here it's not really large, but it's more like we are doing a lot of redundant memory accesses that we should not be doing here, right? So for that, sometimes it is better to use this representation. Let's say when L is small, right? So if L is small, then let's say L is less than or equal to 100, then we use that one. Otherwise, we will continue using our operations in our constraint matrix, right? So when L is small, up to 100, then we put everything into our graph adjacency list, right? So if you have studied graph theory, then this is a way to represent our graph edges, right? So we only list down the edges, which is U to V, right? So we don't even need the other direction. So if this is the lower index, then we store U to V edge just like that. Okay, so yeah, if we store it like this, then significantly our number of memory access will reduce, but then our storage will increase. So this we will only do it when we have smaller clicks, right? So For smaller clicks, all of them goes into a graph, and then from graph we find the merging of those clicks, and that's how we find this merging, right? So all of this is kind of interesting details, and disabling click merging basically, you know, increases the running time by, I don't know, let's check, 14%, not 20. Okay, so it is 14%. Okay, so yeah, so that's a big improvement on problems that require at least 10 seconds to solve, right? So this is a lot larger than the previous Presolve rule. So that's click merging. So to conclude, what all things we covered in today's video: one, we covered bound and coefficient strengthening, and click merging. Right, so these two things we covered in our today's video, and in the next parts we will cover multiple variables at a time, and see you in the next part.